we're going to take a look for exam 5 at chapter 7 in your textbook. And you've been introduced to a little bit about atomic structure, like what the atom is made up, what the nucleus is made up, where those discoveries brought us to a certain point. Now we're going to look at the atom in terms of what makes it tick chemically. So this is going to be largely constructed of theories and explanations about the way the electrons work in an atom, because that's where the chemistry happens. And then we're going to use that information to explain various aspects of the periodic chart, because it didn't get laid out like that by accident. There's a purpose in the way it's constructed. Okay, so it'd help if I turn that on. And, over here. There we go. All right. How do we know what electrons are doing in an atom? The first clue is color, light. In fact, that's the biggest clue. Everything we know about the whole universe, except for a very small local area out to, well, I guess by now, beyond Pluto, we've explored physically. But everything else in the universe we know from light. And we're starting to gain some information from gravity detectors, right? But that's in its infancy. Most of what we know about the universe is delivered to us through light. So we need to know something about light. What does it mean? How do we wrap our minds around it? And one of the first indications I had, most people have, about the ooh-ah factor of light is fireworks. How do they get those colors? Right? Well, it all happens in the movement of electrons in the vicinity of the nucleus of an atom. That's why do we get the colors, right? We'll see various colors. Potassium is a nice kind of a pinkish color. Sodium is more orange. Zinc is yellow. They left out, let's see, what's one of my favorite ones? Strontium. Strontium gives you a hot pink. When I was working in research, we had this instrument called it's gone blank. Spectrophotometer. And what we would do was we'd pass our samples in solution, and they'd get sucked up into a flame, and the flame would atomize the samples, and then we would shine a light through them of a particular wavelength that was selective for the element. And it would tell us, after we calibrated it, how much of that element was in our sample. Well, that's the money-making part of the machine. We also used to use it for tours. We'd have school kids come through on tours, and we'd aspirate these different elements through them, and they just, I mean, it's like fireworks. You get these bright colors, different colors. And one of their favorites was strontium because it was a hot pink. So the question for us is, why do these different elements give us different colors? Actually, there are a number of ways that you can get colors out of not just elements, but different compounds. And it all has to do with the way the electrons move, how they move in relationship to the nucleus. Some chemicals give us different colors when they're in the flame than they do when they're in solution. Let's see. No, they don't have copper up there. Copper would be a different color in solution. And there's a chemistry going on there, how the copper compound interacts with water molecules versus how it would behave in a flame, whereas it's free atoms being excited by the flame. Okay, these are various questions. Everybody knows that blood that comes out of an artery is bright red, and blood that comes out of a vein is kind of a purplish color. I mean, it may look reddish to begin with, but actually, when it first comes out, it's kind of purplish color because it's depleted of oxygen in the veins. But as soon as oxygen hits it, that oxygen attaches itself to the hemoglobin in the molecule, and particularly with the iron. And oxygen and iron together, it's like rust. Like rust is a brick red. So our blood is rusty when it's oxygenated. I did my master's research on crawfish, the crawfish processing waste. In Louisiana, the crawfish industry is huge. There's a very large fresh crawfish market. A lot of it comes out of the Atchafalaya Basin, but growing in competition is farm-raised crawfish, rice farmers in particular. When they finished harvesting their crop, they've had to drain the crop, drain the fields, and let it dry out so they can harvest their crop, and then they reflood them. And when they reflood them, the crawfish that are already there in the ground build their little chimneys. I don't know if you've ever seen these, but some of those chimneys they build are this high. They throw the mud out from underneath down in their holes, and then just make a chimney out of it. But their shells are red, and it's due primarily to this compound, astaxanthin. And you'll notice in here, it's hard to see, I know, but there are alternating single and double bonds. Okay, those are conjugated bonds, and they have a special effect on the energies of the electrons that are in that molecule. And the more of them you have together, the lower the wavelength that they will absorb. Right, so I'm not going to beat that horse anymore. We'll move on. So the key to understanding the atom is really in the electromagnetic radiation, light. So we need to know something about light. Right? This is not a physics class, but you're going to get a little physics anyway. So these are three characteristics of actually any type of wave, but now we're focusing on light, is the wavelength, and we give it a symbol, the small Greek letter lambda, which is wavelength, which means, which stands for the distance between two crests on a wave. So if you visualize your wave like this, then from here to here is a wavelength. And in standard SI units, that would be meters. Okay. The next characteristic we give, some textbooks use an F for frequency, because most students kind of freak out at the Greek letter that we typically use, which is the Greek letter nu. In English, we write that NU. That stands for frequency. Frequency is how many of these crests pass a given point in 1 second. Okay? So it's per second. second to the -1. How many crests pass that point in 1 second? That's the frequency. And we also give that a special name. It's called hertz. And hertz can be written as cycles per second. And cycles is actually not a dimension. It's just we put it in there because it helps us understand that whatever is happening is relative to 1 second in time. The actual unit of the frequency is simply reciprocal seconds. Okay, then there's the speed or velocity. And in the case of light, we give it a special term, a small c. And the small c stands for how fast is that light wave moving. Okay? So if you look at this, and then a second later, it's down there somewhere, it's gone so many meters per second. Okay? And light in a vacuum travels at 2.9979 times 10 to the 8th meters in a second. So it's, as my daddy used to say, lickety split. It is fast. Now that's in a vacuum. And for making measurements in the air, in the Earth's atmosphere, it's pretty close. Right? In fact, sometimes we round it off to 3.0. But just realize that light travels at different speeds through different media. Right? So that's why we can wear lenses that bend the light, because once light encounters the lens, it slows down. And if you curve it just right, part of the wave slows down more than the other, and it makes the whole wave bend. That's called refraction. We'll talk about that. I think we get to that in a little bit. Or maybe I might be mixing up my other courses with this. It's hard to keep them straight. Okay, so wavelength is lambda, frequency is nu, speed is c. And they're all related by this one equation. Speed of light is equal to its wavelength times its frequency. And if you do some dimensional analysis, if you look at the units of measure, this is a meter, and this is a reciprocal second. Right? So that times that has to equal meters per second. All right, so this is artist representation. This one has a longer wavelength than this one, and this one has a longer wavelength than that one. Notice that when the wavelength gets shorter, the frequency gets higher. Right? They're inversely proportional. And like I've said before, I don't know if you remember, but if you have two variables that are equal to a constant, just like this, that's a variable, and this is constant. So if this one goes up, that one has to go down, and vice versa. That one gets shorter, this one gets longer, it's bigger. If this one gets longer, then that one gets shorter. Okay, the electromagnetic spectrum covers a lot of territory. Our eyes are only responsive to a very narrow range of wavelengths. That's the purpose of this slide. We can see light that is in the wavelengths here between 4 times 10 to the minus 7th and 7 times 10 to the minus 7th meters. Okay. And very often when we report wavelengths of light, it's more convenient to use a different unit of measure than the meter, right? Because otherwise you've got to use this scientific notation. But if we go, if we use the nanometer, right? Remember, nano is 10 to the minus ninth meter. If we use the nanometer, then the range of wavelength that we can detect with our eyes is between 400 and 700 nanometers. Okay, and this is an expansion, a blow up of that region. And I don't know if you've had this in high school or in grade school, memorizing the colors of the rainbow. Remember the Roy G. Biv? Yeah. Red, orange, yellow, green, blue, indigo, violet. I can always find violet and I can always find blue, but I never have been able to find indigo. It's stuck right in here somewhere, I think. But you'll notice that the red end is the longer wavelength. So it has the smaller frequency. And the blue end has the shorter wavelength, or the larger frequency. Now, this is important because the energy that's carried in a particular frequency of light is dependent upon that frequency. The higher the frequency, the more energy is contained in the light that passes this point. So the higher energy end of the spectrum is down here. Right? Down here for visible light, down here for the whole spectrum. The lower energy range is up here, or for visible light in the red end. Okay. And it's spread out, and we've chopped it up into pieces that are a little easier to manage. On the lower energy end of the spectrum, we go from red to infrared, which means less than infra. And microwaves have less energy than infrared. They're longer wavelengths. And then you get into the radio wave range. And they have very, very long wavelengths. I know in the mornings before the sun comes up, I'm on my way to Logan, I can pick up AM 750 out of Atlanta. So I listen to that because you can't get anything else back in those mountains. So I know what the traffic is doing in Atlanta. And that's another topic. Why can I get that there? And you can't get FM there, but you can get AM. And there's a reason for that. Maybe we'll run across that later, but if not, we'll take a special lecture. Okay, we use microwaves for communications. We heat our food with them. Infrared radiation. We keep our food warm, right, before it's brought out to our table or before we buy the fries at McDonald's. They keep them under an infrared lamp. These are often called heat waves. The ultraviolet side is higher energy or shorter wavelength than the violet end. So ultraviolet is an appropriate name. And certain wavelengths of ultraviolet can do damage. They can damage your skin. That's what a tan is. It's your skin's response to damage. X-rays are even higher energy, and they can penetrate through our bodies, and they're often used for non-invasive diagnostics. They can see broken bones. They're good enough now. CT scans, computer-aided tomography, X-rays, can see structures in your body. Gamma rays. These are the highest energy, shortest wavelength light beams in the universe. And they are produced only under very, very violent conditions. Except, on a planetary or a cosmic scale, that's true. Gamma rays can also be emitted by disintegrating nuclei, undergoing fusion or fission. Okay, but they're very high energy. And some of the gamma ray bursts that come from way yonder, if they're directed at us, they're very narrow beamed. But if they happen to be directed into our space, even though they're light years away, they can like strip our planet of its atmosphere. So we've been lucky so far. At least in human civilization terms, we haven't seen one. We've seen the results, and we picked up what would you call it? Penumbras of the beam. So we know that they're out there, and we can gauge how energetic they are, but they're very dangerous. Okay. So how do we get light? Right? In order to get light, energy has to be transferred some way or other. If you add energy to an atom, you can detect the absorption of that energy in the atom. And that's what I did with that instrument, the atomic absorption spectrophotometer is the proper name. We detected the absorption of light by atoms in that flame, and we knew how intense the beam was on this side. We knew how intense the beam was on the other side, and we could ratio them, and that told us how much of that element was in the flame. But you can also add energy other ways, like with this pickle, we're running a high voltage direct current through it. And when we heat the atoms up in that pickle, they give off energy as light. So remember, energy can't be created or destroyed. It can only be transformed. So when we put energy into that pickle, it's got to do something. It's got to go somewhere. A lot of it goes into heat. Right? So I wouldn't want to eat that pickle after we did anything to it like this. But some of the energy is emitted as light. And we're going to find out why that is in just a few seconds. Oops, wrong button. Okay, what do we know about light? Well, we know a lot about light, but there's still major controversies about the nature of light. Beginning in sometime in the 18th century, the wave nature of light based upon these concepts that we've given so far, C equals lambda nu. Based upon that nature of light, a brilliant mathematician by the name of James Clerk Maxwell derived a set of equations that would describe electromagnetic radiation. And they work perfectly well, right? As long as you considered light a wave. As long as it was a wave, these equations work great. And they're still valid today, like I say, as long as you're considering light a wave. And to a certain extent, they agree with some of the concepts proposed by Einstein in the general relativity theory and later quantum mechanics. I mean, they have their limitations, but as long as the wave nature is under investigation, these equations work great. We're not going to worry about the equations themselves. This is sort of a history lesson. So much so, we thought we understood light, that at the beginning of the 20th century, scientists believed that they understood everything they needed to know about the universe. All that was going to happen from then on was just refinements. Right? But they were wrong. Along comes Max Planck, and I believe he was a German. He was studying the phenomenon of black body radiation. What that means is that if you know the temperature of an object. And the object itself is not undergoing any type of reactions, nuclear or chemical reaction. It's just a black body, like a ball of compressed carbon. And you heat it up. If you heat it up to a certain temperature, it will radiate light of a given wavelength. If you make it hotter, then the wavelength will shorten. It'll go from red to orange. It'll go through the spectrum. That's black body radiation. And that's how we tell, we use that information to determine what is the temperature on the surface of any star in the universe. We just say, all right, what color is it emitting? And we relate that to the temperature that it would have to be as a black body to radiate. Max Planck did some other things too. He devised an equation, it's on the next slide, but I'm going to write it up here anyway, to determine the energy of a packet of light. He was starting to introduce the concept of quantum, a quanta of light, a packet of light. And he said that packet contains energy that's proportional to its frequency. Okay? So here are your two variables. Here's the constant. This is Planck's constant. You don't have to memorize it. It's in the useful information. If we rearrange that, Planck's constant is equal to energy divided by frequency, right? And I've said this before, if that's a constant and these are in the relationship of a quotient, then it's a direct relationship. So the higher the frequency, the higher the energy. Okay, so now we're going from the wave nature of light, and we're starting to investigate something that the 19th century scientists never conceived, was the particle nature. So, as it turns out, it depends on what you're studying as to whether you treat light as a particle or a wave. For the longest time, scientists will argue back and forth and say, wave, particle, and they got some pretty heated debates. Eventually, they just threw up their hands and said, okay, it's both. That's how perplexing the problem is. Light can either be a wave or a particle, depending on what it's doing and how you're measuring it. Okay, so there's our Planck's equation, right? The energy of a photon, that quanta is called a photon. So that's where Star Trek gets their photon torpedoes. I don't know. Am I going too far back? They still use them, don't they? Star Trek? Yeah. Star Trek movies. Right, I'm talking about the original Star Trek series with Captain James T. Kirk. Anyway, this is one way to write the equation like I did before, but since C equals lambda nu, we can solve this equation for nu, and that's C divided by lambda. Now, Planck's equation can also be the constant, and then substitute this for nu, C over lambda. So if you know lambda, you just use the speed of light and you get the same results. And there's Planck's constant. Constants, any type of physical constant that's calculated in the physics or chemistry, there's no logic to it. It's sort of I look at it as a grand fudge factor. In other words, the units of measure here need to be certain type of unit, the joule, for instance. And these units typically are in reciprocal seconds. So the Planck's constant is simply a way to get from this one to that one. Right? So these constants, these physical constants, are typically kind of weird. right? This one is joule seconds, units. Now the speed of light, that's a different story. Actually, in that case, the constant came before the others. In other words, you didn't have to invent the speed of light to be it. You just had to recognize the relationship of the constant to these other factors. Oh, I got a video. All right, let me see. I think I had to do this manually. Get it started.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also—
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay, let's see. So, did you catch what the photoelectric effect was? I know they didn't explain it in a lot of detail, but what it means is that this packet that strikes the surface of a metal will eject an electron only if it has enough energy. The wave theory of light says that the more intense the beam, the higher the energy. So they thought that at any wavelength, they just make it a stronger beam and you get electrons ejected, but it didn't work that way. That was the problem. It was the amount of energy that was contained in the beam of light based upon the particle energy, the photon energy. So some metals will eject light with orange wavelengths. Some won't eject light until you get to the violet, and some won't even eject until you get to the ultraviolet. So you need more and more energy in that photon in order to get electrons ejected. And that's the basis of our solar panels, the photoelectric effect. Okay. So what does the photoelectric effect have to do with the quantum nature of light? Oh, I already told you that. I was stealing my own thunder. Right? No electrons are emitted below a certain threshold frequency, right here, V sub 0. Actually, this is new. It looks like V, but it's kind of a slanted V. And it's characteristic of each metal. Below that frequency, no electrons are emitted. Doesn't matter how intense the light. And if there's enough energy in the photon to eject the electron exactly, it just leaves the surface and sits there. That is the threshold frequency. But if the frequency is much shorter, much higher, shorter wavelength, higher frequency, then it uses a portion of that energy to eject the electron, and what's left over goes into kinetic energy for the electron. It just makes it go faster. I think that's what this one is getting at. Oh, no, this one, once you've got the electron ejected, all the intensity does, if you make the light stronger, is it ejects more electrons. But it doesn't eject any electrons unless it reaches that value or higher energy than that. Okay, number 4, that's the one I was getting at. The kinetic energy of the ejected electron increases with the frequency of light beyond the threshold frequency. Okay, so the conclusion is that electromagnetic radiation must arrive at the surface of the metal in discrete packets, photons. And each quantum of light has to possess this minimum amount of energy in order to excite the electron to a level where it will be ejected from the atom, its parent atom. Anything less than that are called thermal photons, right? So when they're absorbed by the metal, which they must be, they're either absorbed or reflected. But if they're absorbed, then all they do is heat the metal up. It doesn't eject any electrons. Okay, I mentioned that one already. Right, so intensity of light is a measure of photon density. In other words, you pack more photons together in a period of time as they strike the surface. That's an increase in intensity. It's often referred to as photon flux. Okay, so what does the photoelectric effect tell us about the structure of the atom? That's where we're headed. We want to know, what does this information tell us about the atom itself? The interaction that occurs between matter and light is with the electrons, not the nucleus. The electrons are where light interacts with atoms. And the absorption of this photon of light is tuned to the movement of electrons in the atom. In other words, when you've got a nucleus here and you've got an electron here, its energy is relative to the nucleus. So this electron will have a certain amount of energy relative to the nucleus. This electron would have more energy. And the way to think about that is, what does it take to get it to go from here to here? If it's being held by the nucleus, you've got to put energy in. Right? There's Planck's thing. You often see it written this way. H nu means energy. Put energy in, then it can move to further away from the nucleus. So that means it's higher energy here than it is here because we had to put energy in to get it there. And there's no in between, right? When it goes from this level to this level, this has to match it perfectly to make it go there. Okay, this threshold energy that we're talking about for a photoelectric effect, this is the energy it takes to go from actually the highest level to infinity. Right? It frees the electron from the atom itself. How much energy does it take? And for this is the one instance where the energy of the photon can be parsed. In other words, enough energy to get it to infinity, and then the rest of it is kinetic energy. But between levels around the atom, those things are quantized. That is, if you don't have the exact amount of energy required to go from here to here, then it won't happen. That's why we can shine light through those atoms in my flame, in my spectrophotometer, and it's selective for a given element because the electrons in that element move from here to here, and that's empirically determined. But all the other elements ignore it because it's exactly tuned to that electron movement for that element. Okay. Right. This is sort of a side note. If those electrons have kinetic energy, then they must have mass. Right. That's my favorite picture of Albert Einstein in his later years. He'd already made a name for himself. He was pretty secure, so he could make funny faces if he wanted to. So he came up with a special theory of relativity in 1905. But he didn't win the Nobel Prize for the photoelectric effect until, was it 1920? No, 21. So it takes a while. The Nobel committees, they always lag behind several decades because they want to be sure that what they're awarding a prize for is valid. It has to stand the test of time and scrutiny by other of his peers. Okay, so the special theory of relativity actually proved mathematically that light has mass. In fact, everything, all energy can be considered as either mass or energy. Either way, it's interchangeable. Right? This is what he said. Right? Mass times the speed of light squared tells you how much energy is contained in that mass. But he's talking in terms of relativistic mass, and the nuances in rest mass versus relativistic is it's a difficult subject even for physics class. So I'm not gonna beat that one. It's just, what do we mean by relativistic? Usually, just think of something moving very fast, very close to the speed of light. That's relativistic. Rest mass is like me, standing here. So I guess I have a different relativistic mass than I do a rest mass. Okay. There were other scientists. It's a funny thing, physics is divided into two universes. One is theoretical physics and the other is experimental physics. Some physicists have a knack for experimental physics, whereas people like Einstein are more cerebral. I mean, they think up these theories, and then they leave it to the experimental physicists to prove it or disprove it. But Arthur Compton was an experimental physicist, and he actually confirmed the particulate nature of light. For Einstein's theory. Now we have electromagnetic radiation that has wave properties and particle properties. And in fact, that can be expanded to include all matter. All matter has wave properties and particle properties, right? When we get to be this big, matter this big, we generally think of ourselves as only particles. But we do have a wave, a calculated wave for us, which is called the de Broglie wave. And that can be calculated for subatomic particles or for you and me. Depends on how fast we're going. So, which is correct? They both are. Okay, how about the wave nature of light? What is it that supports the wave nature? Well, one of the things that supports the wave nature of light is the process called diffraction. Diffraction is the characteristic of light that allows it to peek around corners, right? If light were only particle, then if you have a wall here and you shine a light beam here, then it's going to be dark over here and light over here, because it'll go straight across and this will be completely black. Right? But we know that's not true. I mean, anytime you've gone through a lunar eclipse, you know that you see the moon, it doesn't have a sharp line where the earth cuts off the light and it's black on one side and light on the other. It's kind of graded. Now there are two effects there. That's a bad example. It's both diffraction and refraction because of our atmosphere. Let me get back to diffraction then. So what happens is that when light strikes this edge serves as a point source for the wave. Right? The wave strikes it here, and this serves as a point source for the wave to do that. That's why it's really dark down here, but it gets lighter and lighter and lighter until we get to here, and then lighter still, and then it grades off again. So the brightest point is right in here. That's diffraction, and this is a demonstration of diffraction. We have a wave originating, striking. Think of this as ripples on a body of water. And when the wave strikes this point, it serves as a point of origin for the new wave. That's diffraction. That is only characteristic of waves. Refraction, that's diffraction. Refraction is the bending of light as it passes from one medium to another. Now, if one of the mediums is opaque, then, there's no refraction. It has to be at least translucent. So that's why we look at the lenses. So if we have air on top and glass on the bottom, and here's normal to the surface, right? This is a right angle. Then if light is coming in as wave here, right, then it'll slow down, but it won't change direction because it's on the normal. But if we slant it over a little bit like this, and we say the wave is coming down here with these crests, right? Okay, what happens is when it reaches the surface of the glass, it slows down. Right? So it slows down, that means it's going to be like that. It has to slow down. So that side of the wave slows down. It's kind of like the Ben-Hur chariot race. Right? You have one horse on the inside. He's the slow, steady one. And you have the fast one on the outside. And he just races around the outside of the curve. That's like light. So here's the slow one. When it hits the glass, it bends the light like that. That's refraction. And it only happens for waves. Okay. Now let's inch our way toward structure of the atom, the electronic structure of the atom. We got a few more minutes. Light that comes from the sun is what we call continuous spectrum. In other words, you can run it through a prism and there's no break, right? You see color, 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 and nothing in between. That's a continuous spectrum. It supposedly has every wavelength that's available contained in light. We just have to break it apart to see it. What you see from individual elements is what is called a line spectrum. So if you take the light coming from one of the elements, hydrogen's the easiest one to do because it's only got one electron. It will be a line spectrum. In other words, when you run it through a prism, it spreads it apart and you can see the individual lines and they are separated. So you have a line at this wavelength, one at this wavelength, one at that one, and one at that one. And that's what got the curiosity up for scientists. Why is it like that? I mean, why is it continuous? If you heat something up, right, shouldn't you get a continuous spectrum? Well, they misunderstood the continuous spectrum from the sun. The continuous spectrum from the sun is an accumulation of heat, energy transformations, all kinds of things that go together into one light beam that reaches the Earth. Right? If you look at individual atoms from the sun, you will see line spectrum. In fact, that's how helium was discovered first. Helium was discovered in the atmosphere of the sun before it was discovered on Earth, spectroscopically. Okay, so this line spectrum is characteristic of individual elements, and hydrogen is the simplest because it only has one electron. So this used to be a flash video before support for flash was stolen from us. But I did want to leave this one up here, this introductory slide, even though it's not a video now, to show you that this is a continuous spectrum. See, it's just like that. And if your spectrograph is properly calibrated, you can tell the wavelength of each one of those wherever you stop along the way. This is what we call white light. Now, white light can be simulated, right, with the primary colors. And depending on whether it's emission or reflection, we won't go into that. But you can fool the eyes into thinking, or fool the brain into thinking that it's white light when it's not. That's the whole purpose behind, say, printers with 3 or 4 or 5 colors built in. You mix the colors and it looks like this color or that color or even white. But in spectroscopic terms, white light is every color.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay, I wrote these up here. These are the 4 visible lines for hydrogen discharge. Now, it's discharging in non-visible regions like the infrared and the ultraviolet or further, because these transitions, these energy levels around the atom, these electron energy levels, n equals 1 is the closest you can get. And that would be the rest state for neutral hydrogen. The electron would be here. But if we excite it, then we get transitions between 3,2, 4,2, 5,2, and 6,2, give us the visible range. If they go from these levels down to 1, then you're probably in the ultraviolet. There's more energy released by those jumps. Notice that between 1 and 2 is a big jump. And then the further you go up, the jumps are smaller and smaller and smaller. So these are not the only wavelengths of emission for hydrogen or any atom for that matter. They're just the ones that we can see. Okay. All right, so only certain energies are allowed for the electron in the hydrogen atom. And these are the energies. And these energies, these jumps, can be used to calculate how much energy that is, right? Because we know the wavelength, we know the speed of light, and we have Planck's constant, we can calculate the energy for each of these transitions. This is going to be the lowest energy transition, the next, and the highest energy transition in that group. And this idea of quantized energy has informed the theories that are used to describe the electronic structure of the atom. This information here is where we got started. Okay, this light is not white for hydrogen. It's a line spectrum. Right? So here's how it supports the idea of quantized energy. If the levels were not quantized, we would see white light because the electrons could move continuously anywhere they wanted to. And when they move from here to here, you get that wavelength. Move from here to here, that wavelength. It just be a hodgepodge. Right? So that's the first line of reasoning that supports quantized electron movements. And because there are only certain colors that are observed, that means that you have certain energy levels that are allowed. So we can say that these energy levels are the only ones that are allowed in the hydrogen atom. All right. So Niels Bohr, who was a Danish physicist, he was a theoretical physicist. So he chummed around with all the big wigs like Einstein and that group. Anyway, actually, I think the proper word is they conferenced together. He proposed a model for the hydrogen atom. That's what the Bohr model is. It only works for the hydrogen atom or atoms like the hydrogen. And I'll explain what I mean about that later. As much time as we have. Bohr modeled his atom after planetary systems. He said the sun is the nucleus and the electrons are in planetary orbits. And we know now that that's not true, but it was the place to start. Right? And it set us on the right track toward actually finding out what the electrons really were doing in the atom. So Bohr's model had these energy levels that correspond here based upon this evidence. And he gave the energy levels numbers, right? The lowest energy level is 1, and then 2, and then 3. Keep it simple. The ground state is energy level 1. The electron won't get any closer to the nucleus than energy level 1. So here's an energy level diagram like the one we saw before, only this one is a little more accurate, I think. The jump from 1 to 2 is huge. And then they only show three of the wavelengths here, 5, 4, and 3 to 2. They don't show 6 to 2. And that's another reason that these seem to be so close together, like they're all in the 400s, and then you jump to 6 because of the difference in the jumps. Right? These jumps are very close to one another. 6, 5, and 4 are very close. That's why the numbers are so close. All right, so the fourth emission line is missing, obviously. Here's another way of looking at the atom, the Bohr model of atom. This is the nucleus, I think. No, this is not the nucleus. This is the energy level 1. Nucleus is right in here. It's so small we don't even put it on the diagram. And when the electrons jump from a higher level to a lower level, they emit light. But they can go the other way around too, like for my absorption instrument. But they can absorb light. They can absorb light of a particular wavelength, right? Maybe one of these wavelengths. And it caused the electron to jump from a lower to a higher level. And that energy goes into the jump. So you can have an absorption spectrum also. If you shine white light through atomized hydrogen in a tube, then it will produce a dark line spectrum on the other side, where you have all this bright stuff and then missing lines. And that's another technique that's used by astronomers to see what's in the atmosphere of stars, because the light coming from underneath is shining through the atmosphere of the star and absorbing. Certain elements are absorbing those light wavelengths, and they can tell what elements are in the atmosphere. They use this on flybys of the planets too, like Pluto. They discovered that Pluto has an atmosphere because let's see, what was it called? New Horizons spacecraft turned around after it passed Pluto and looked through the atmosphere at the sun. And you could tell by the absorption spectrum of the light coming through the atmosphere of Pluto what it's made of. All right. So we want to calculate the energy of an electron for an energy level. So this is Bohr's equation. It's derived from Planck's equation. I don't think that's not Planck's constant, I don't believe. Or is it? Maybe it is. Let me see. I don't have it memorized. Where is it? I was looking for yeah, H. Does it say where H is? Here it is. Yeah, that's not Planck's constant. We'll call it Bohr's constant until they tell us different. So this equation will tell you the energy level of any energy level in an atom that is like hydrogen. Z is just like it was with our discussion of the atom, right? And you have a Z here, number of protons. You have an A there, the number of protons plus neutrons. So that Z is the number of protons in your atom. But it can only have one electron surrounding that atom. So here's what I mean by that. This is a hydrogen atom. Right? This is a hydrogen-like atom, but it's made of helium. So the Z here is 1, the Z here is 2, lithium is next. It would have to be a 2+ because it has 3 electrons. You got to get rid of 2 of them. You can only have 1 electron. All right, so there's your Z's, and then you can calculate the energy for each of these levels. So it depends on the Z number, and it depends on which one you're looking for. You want to know 1, 2, 3, 4, whichever case it may be. And you can find the energy of that. particularly level. Now, this tells you the energy for each of the levels, right? Like there's 1, and there's 2, and there's 3. So if we know the energy level of this one, and we know the energy level of that one, all we have to do is subtract one from the other, and we find out what's the energy of the jump. And if it jumps from, say, here to here, the electron goes from here to here, then we know it's going to give off energy. And we can calculate by subtracting the lower energy from the higher energy. Let's see. And the energy is calculated in joules. Oh, okay. When you go to infinity, that's energy level equals 0. So anything closer to the nucleus is more negative. Okay, just by convention. All right, oops. There we go. So this would be the energy of electron for a hydrogen atom. Notice that we've only got 1 here, C1. So what if we jump the electron from one energy level to another? Right? We say, all right, it's like the delta calculation is always final minus initial. So this is the final initial, this is the final energy of the electron. And this is the initial energy of the electron. So you subtract the initial from the final. And if it goes one way, it'll be positive. If it goes the other way, it'll be negative. And you can tell from the sign whether it's absorbing or emitting. And we can use a little algebra, right? We factored this one out here, put it outside. So now on the inside, all you need to know is if this is a hydrogen atom, it's 1 over n squared final minus 1 over n squared initial. There it is. That's a simplified version for just the hydrogen atom. Okay, so for this, I got 5 minutes. Let me see how much more I got to get to a break. I'm close. I'm close. Let's see how far I can get. Okay, so if here's our formula, and the transition is from 5 to 2. 2 is the final, 5 is the initial. Right? So 2 is going to be the final, initial will be 5, and the change in energy is this many joules. Right? And we know that it went from it went from high energy to low energy, so it's giving off energy. And that gives us a negative value. We can think of this in terms of our system versus surroundings. If it's negative, then the energy is being lost. Just like heat. So a negative Q would be exothermic. A negative delta E for this would be exergonic. I think this is the proper term. So exiting energy from the atom. If it were positive, then it would be absorbing energy. Okay. Now, if we take, if we know the wavelength here, and we convert the wavelength to meters, right? So this would be, nanometers would be 10 to the minus 7 meters here. Wavelength, and we have C here. Right? So this is the frequency right, over here in Planck's equation. And this is Planck's constant, Then we calculate that the energy should be 4.577 times 10 to the minus 19th joules, and it's pretty damn close. Right, within very small experimental error. Okay, back to the Bohr model. It does fit the quantized energy levels for the hydrogen atom and postulates circular orbits. And by convention, we find that the energy becomes more negative relative to the free electron state. So the more negative it is, the closer it is to the nucleus. But unfortunately, Bohr's model is not correct. Electrons do not follow circular orbits. One of the things that negates the circular orbit model, and they probably thought of this at the beginning, but they had to sort of put it on the back burner because the model itself was working to a certain extent, was when you have something in orbit around, it's bleeding energy. And the electrons in circular orbit should eventually spiral into the nucleus. So what color of light is emitted when an excited electron and hydrogen falls from? All right, so that's the shorter wavelength, the bigger jump, not so big a jump, even less jump, and a smaller jump. So that one has the color light that, what color of light is emitted when it, oh, okay. That's the lowest energy jump from 3 to 2 in that group. So that's the longest wavelength. Remember, longer wavelength means lower energy. Longer wavelength means smaller frequency. Did I lose somebody? Oh, Kyra must have jumped off. Jump back in. Let's see, did I miss counting somebody? Kyra, Justin, Brittany. No, Emma never showed up, I guess. Okay. Well, I guess we can pick it up here. I was hoping to get to the quantum mechanical model, but this will be a good place to pick it up. We'll pick it up with Heisenberg